I'm at the top of the second page of your notes handout for 3.1. There's a typo on that. The page says an alternative definition of the derivative of f at c. It should be of the derivative of f at a. So that little italic c on your paper should be an a. So this is an expression for another way to say the derivative of a function, but instead of giving a whole function that's a derivative, this just computes the derivative at one single point. So you can see the connection to the formula, that same formula we learned at the end of in 2.4, because there we always gave one specific x value we cared about. So this is the same idea here. And if you work on example A, I'm going to tell you right now, the answer should be -1 over a squared. You're going to arrive at it almost exactly the same way we reviewed that problem that we did in 2.4 that we reviewed at the beginning of the first video from 3.1. So remember, the derivative is a formula, a function that gives the slope of another function at any x value. So given an example like this, here I have a piecewise function for f of x. Clearly each piece is linear. I can give an expression, or I could give a picture of the derivative of f, which I call f prime of x, by just figuring out in my head. I don't have to do the math with the limit expression like I did in the last couple slides. Because I know about the slopes of lines, this is not going to be difficult to find the slope for each piece of this piecewise function. So consider the first piece. The first thing that f of x does is it increases. And can I figure out the slope of that line? Well, I'm going to do change in y over change in x. So this is like 1, 2 and 0, 0. So 2 minus 0 over 1 minus 0. I have a slope of 2. So anywhere between 0 and 1, the slope of the graph was 2, which means anywhere between 0 and 1, I want to show that the slope is 2. So that's why I've graphed here this little horizontal line segment at y equals 2. And then, once I get to x equals 1, my original function changes. It's still linear, but it's different linear. It's linear with a different behavior. So the second piece in this piecewise function seems to last from about x equals 1 to x equals 4. And what's the slope of that line segment? Well, I'm going to change in y over change in x, or rise over run. So I went up one space and over 1, 2, 3. So looks like a slope of 1/3. So here, my slope is 1/3. Anywhere between is 1 and 4 on my original graph. The function had a slope of 1/3. So this is the horizontal line segment at y equals 1/3. That's a 3. So notice something here. That first piece, nobody was fighting over the behavior of the function at x equals 0. The function wasn't even defined to the left of x equals 0. So just like I would say the limit of f of x is defined at x equals 0, even though I only have a limit from the right, it's because nobody's even trying to find a limit from the left. I can also say that my derivative, nobody was fighting over the behavior, the slope of this little line segment from the left, because the function doesn't exist toward the left. So that's why I got to color in that 2 up there. But now look at it, x equals 1. I didn't color in either dot. Remember where the limit comes from. Remember where the derivative comes from. Its formal definition, it's a limit expression. Well, for a limit to exist, the limit from the left has to equal the limit from the right. So for a derivative to exist, the derivative, which is a limit, from the left has to equal the derivative, which is a limit, from the right. And notice that as I was approaching x equals 1 from the left, my graph had a slope of 3. My graph had a slope of 2. And as I was approaching x equals 1 from the right, my graph has a slope of 1/3. Those limits are different, which means that the function f of x, well, the function f prime of x, does not have a value at x equals 1. I can't pick the limit from the left, I can't pick the limit from the right, because how could I decide which one to choose? So just notice that at these points where the slope from the left and the slope from the right are not equal to each other, I won't be able to color in a point on my derivative. So similarly here, when x, my next piece is here between 4 and 6, it's a horizontal line segment, so its slope is 0. That's why I've graphed here y equals 0 between 4 and 6. Notice right at 4, as I came from the left, the slope was 1/3. As I come toward 4 from the right, the slope is 0. Those limits, those derivatives don't match, so that's why I have to leave open circles for both of these. And then notice here the last piece. This is the first piece of my piecewise function that goes downhill, for which f of x is decreasing. Notice that means, for me, I have a negative slope. And again, I can use rise over run to find that negative slope. Looks like -1. So you can see here I've drawn in the slope of -1. So now I'm going to show you. I know the picture's a little fuzzy on your handout. So this is question 26 from page 107. You can copy it in a little bit on your better on your paper. You're going to tell me, you're going to give a picture of f prime of x. So it should be a bunch of horizontal line segments that you figure out by finding the slope of each piece of this piecewise function. And then tell me at what x values there is no derivative. At what x values did you have to leave an open circle, maybe at both ends of a line segment.